really need is you need to have this sort of half of an electron gas. And so, so if you have an ordinary semiconducting material that has a strong spin orbit, then what it can do is it can give you sort of this Rashba type band structure. Okay, so so if you have a Rashba term, then what it does is it spin splits the energy bands in a way where you have a Kramer's degeneracy at k equals 0, but then it gets split like this. And so the idea then is that if you break time reversal by either applying a magnetic field or by having some magnetic interaction, then what you can do is you can open a gap at this Kramer's degeneracy point, and then if you can put your Fermi energy inside that gap, then you just have a single Fermi surface, which sort of looks like the helical Fermi surface. Okay? And then if you make this superconducting, then that's good enough to make it into a topological superconductor. Okay? So somehow, once you have the topological superconducting state, you can break time reversal. Let's suppose you were doing it with a topological insulator. You make it a superconductor, the surface a superconductor, then you could break time reversal symmetry, and you still have this topological superconducting property. Okay, so the time reversal symmetry wasn't essential to begin with, and so you can do it in this case as well. Okay, and so once this idea was out there, then there are lots of different ways that one can go about trying to do that, and so I think Amir is probably going to talk a little bit more about the experiments here. So there are some experiments that Amir is going to tell you about attempting to do something at least on these quantum spin Hall insulators. So they're not at the point where they can see anything that's related to the Majoranas, though they do see something interesting by making these Josephson junctions mediated by the quantum spin Hall insulator. And then in the one-dimensional system, there are two very promising experiments, one done at Delft and one done here at Princeton, where they have observed what you would want to, the first thing you would want to see when you're looking through the Majoranas, you'd want to see this, you'd want to be able to tunnel into this zero mode. Okay, and so they see a peak in the tunneling density of states, both in these semiconductor quantum wires and also on these atomic chains of ferromagnetic ions sitting on top of a superconductor. And these peaks are what you would want to see if you were looking for a Majorana zero mode. Of course, the challenge for these experiments is to rule out all of the less interesting explanations for what this zero mode is. But I think this is very, very, very promising and exciting experimental development. But as it stands, these experiments are not taking advantage of the thing that is so interesting about these Majorana zero modes. Okay, and so that's a challenge for the future, is to actually do something with these that takes advantage of this sort of non-local way in which the quantum state is stored. Okay. All right. So let's see. I have 5 more minutes left. I have several different things I could do. I think maybe what I'm going to do is just talk about this one last thing. This is something that's a little bit more recent, and I just want to give you a flavor for what could happen if you have strong interactions. So I told you that if you have a topological insulator surface, then you can open an energy gap on it. If you break time reversal symmetry, you get this magnetic state. If you break gauge symmetry, with the particle conservation, then you can get a superconducting state, which opens a gap. And both of those are kind of interesting. Okay? And so then the question is can you open a gap on the surface without breaking any symmetry? Okay? And so let me try to, so let's suppose you could do that. And what I want to show you is what kinds of properties would that state have to have if you could do it. Okay? And so in order to think about that, I want to give you a couple of arguments, simple arguments, and then there's actually been a whole lot of progress in our understanding of this, though I don't think that this progress is yet in its final form. So there may be room for more ways, for simpler ways of thinking about this. But so what I want to imagine first is doing a kind of Laughlin construction argument. Okay, and so what I want to imagine is I have my topological insulator, and first I'm going to surround it by magnetic material. So I open up a magnetic gap on the surface. Okay, so the entire surface is like it's in this quantum Hall state that has a Hall conductance of E squared over 2h. Okay, and so then what I want to do is I want to drill a little hole in the slab and thread a quantum of magnetic flux, just like in Laughlin's argument. And I want to think about what happens. Well, you know that since the surface is a quantum Hall state, that when you thread the flux, that there's going to be a flow of current out the surface, which is going to be exactly a charge of E over 2 has got to flow out the surface. Then it's going to flow around back into the other surface to here. Okay? And so what you know, therefore, is that along this flux line, a charge E over 2 actually has to be transferred from the bottom surface to the top surface. Okay, so that has to happen because, you know, this is all non-interacting electrons. And so at the end of the day, after I've threaded the flux H over E, and everything's gapped, after I've threaded a flux H over E, there can't be any charge E over 2's around because this is all just non-interacting electrons. The only thing I could have is an E. Okay? And so in fact, when you thread an H over 2E flux through a topological insulator, in fact, a charge E over 2 is transferred between the top and the bottom surface. Okay? And so this is actually a sort of a fundamental property of a topological insulator. And one way of saying this actually is to ask, you know, threading a magnetic flux through the topological insulator is sort of the same as taking a magnetic monopole and dragging the magnetic monopole from the bottom to the top. You know, through from the bottom to the top. And so this property is the same as saying that the charge of a magnetic monopole inside a topological insulator is E over 2. Okay, and so this is actually a famous effect, sometimes called the Witten effect, which is that when you have a theta term, that the theta term assigns charge to a magnetic monopole. Okay, and so basically the upshot of this, though, is that when you do this flux threading, a charge E over 2 is transferred from the bottom to the top. So now what I want to do is I want to say, let's suppose that we have some topological, some state that doesn't break any symmetries, doesn't break time reversal symmetry, doesn't break it doesn't break charge conservation, and let's suppose, but it has a gap, and so let's imagine that we have that on the surface now. So now I'm going to do the same argument. I'm going to thread this magnetic flux, and then I can gauge it away, or I can think of it as dragging a magnetic monopole through. Okay? And so then it's still going to be the case that I transfer a charge E over 2 from the bottom to the top. Okay? But now, since I have a gap, and so when I thread the flux, since I have time reversal symmetry, there can be no Hall conductivity on the surface. So that charge just stays put, and it has to be left there at the end. And so in order to have this gapped state, it must be possible to leave a charge E over 2 behind after you're finished. So that means that there have to be eigenstates of this system that have charge E over 2. Okay, and so this surface state, if you have a gap, must support these fractionally charged charge E over 2 excitations. Okay, so this is one argument that it has to be fractionalized. Another argument you can make is you can say, well, let's suppose I had this symmetry respecting gapped state. What would happen if I had a magnetic domain wall? So remember, on this magnetic domain wall, we have to have a chiral Dirac fermion. Okay? And so this chiral Dirac fermion has sort of like a Hall conductance of 1. It also has, it also carries heat, so there's sort of a central charge of 1 that occurs as well. Okay? So this is like just a chiral Dirac fermion. And so what has to happen if so now let's imagine that I put this symmetry respecting gap state in the middle. Then what has to happen is that this chiral Dirac fermion mode has to split in half. Okay, because the top half and the bottom half are really going to be the same as each other, and so half of it has to go this way and half of it has to go this way, and so this edge state has to have a Hall conductance of, has to have a conductance of 1/2, but it has to have C equals 1/2. So it has to somehow split the chiral Dirac fermion into 2. So that means there has to be some chiral Majorana mode associated with this. Okay, and so having this Majorana mode means that this state has to also have some sort of non-abelian topological order as well. It has to be sort of like the Moore-Reed state of the fractional quantum Hall effect. Okay, and so it's an interesting problem to actually figure out what in detail this state looks like, and so this is something where there's actually been a lot of progress, and this actually is turning into a kind of interesting problem, which might be worth thinking about. But I'm out of time, and so I think with that I'm just going to finish. So thank you very much.
We have time for a couple of quick questions.
Does the SRG state spontaneously break time?
Pardon me?
Does the SRG spontaneously break time?
I'm sorry, does which state?
SRG, the symmetry.
Well, I'm assuming it does not. Yeah, so so obviously if I spontaneously break time reversal symmetry, then I'll be back to this. Okay, but I'm asking the question: could there be a state that does not break time reversal symmetry? Okay.
So the 2 plus 1D analog of this, if you add this back scattering term, then even sort of breaks this spontaneously.
I'm sorry. Say.
In the boundary of a quantum spin Hall state,
Yes.
if you add this back scattering term, respects time reversal, then it gaps out, but it eventually.
I'm sorry. Say that again. So
if you have a boundary of a quantum spin Hall at 2 plus 1D.
like this, you're saying? Yeah, like this. Yeah.
So instead of putting this symmetry breaking terms, if you respect symmetry and then add some back scattering terms that gaps these edges. Can you do an analogous thing of SRG in this?
Well, no. So look. So on this, I could imagine putting a time reversal symmetric term in my Hamiltonian, which backscatters a pair of electrons. Okay, and if that dominates, then you're right. I can get into a state where I have spontaneously broken the symmetry. But really, I would say that's really a state that's like this, where then I can I can have domain walls, if you will, between the different signs of the magnetization. And those domain walls are interesting because actually they bind a charge E/2. It's sort of like the domain wall in the Sushri-Verheugen model. Okay, but that really is a spontaneous breaking of the symmetry. That's different than the kind of state that I'm trying to talk about here, where I'm assuming that I'm really not spontaneously breaking the symmetry. I don't know how to do the analog of this in the 2 plus 1 dimensional case. Yeah.
So naively, I think that if you combine any two distinct or different topological phases, you get some sort of a topologically protected edge state of some sort. But are there any general rules? I mean, the last slides you mentioned a couple of designs. I'm just curious if there's any qualitative general rules for combining these different phases and looking at the interface.
Well, so certainly I think in the So for the free fermion cases, I think that's something that one can, yeah, there are general rules. Now, one has to revisit the problem when you allow for strong interactions, okay? And that's a very interesting thing to think about. And I think that is a subject which is not completely finished yet. Yeah.
Take one more.
Okay, yeah, yeah.
So for your TI superconductor devices, would it defeat the point if your superconductor is P-wave?
P-wave with that, just PX wave, not P plus IP. Well, so the problem with that is that you'd have nodes in your in the bulk, right? And so if what you're trying to do is make isolated Majorana modes, then those zero modes would couple to the nodal states in the bulk. So that would be a problem. Yeah.
But it would still be topological?
What?
Would it still be topological in a sense?
Well, so you would not have, so it doesn't have a gap.
Right.
So it's not, if by topological we're talking about topologically classifying gapped states, then no, it's not. Though you can think of the node itself. There's a sense in which that's topological. Okay, so if you have a nodal superconductor, then there's a sense in which you can think about whether the nodes of the superconductor are topologically protected. But that's a different issue than thinking about the topological insulator which has protected boundary states. That's a different use of the word topological.
Okay, I think we can continue questions during the break and during lunch. Catch Professor Kane, he's around. And to thank Professor Kane, we would like to present him with the spaceship. It's a Star Wars stormtrooper.
Wow.
Skyhopper, sorry, not stormtrooper. To take you to far-off places and give you a change of scenery when you think about topological physics.
All right, thank you.